Good afternoon, everyone. My name is Han-Fei Dong from Hainan University in Korea, and my advisor is Professor Simon Song. In this presentation, I'm going to talk about visualization of turbulent kinetic energy on CrossJet flow using magnetic resonance velocimetry. First, I will give you a brief introduction to MRV. MRV is a flow visualization technique that uses a conventional MRI scanner. It measures in a 3D region, and it's a non-invasive technology that doesn't require tracing particles. Because MRV uses magnetic field signals for measurements, it's suitable for complex and opaque flow environments. Furthermore, MRV can measure a wide range of characteristics, including velocity, TKE, temperature, concentration, and Reynolds stress tensor. It was primarily used in the medical field, particularly in applications like the flow inside heart and arteries. Currently, it is also widely used in various engineering flow fields, such as the flow inside the refrigerator. The primary objective of this research is to measure and analyze 3D TKE of CrossJet flow using MRV. First, we measured the stream-wise turbulence intensity in a circular pipe using MRV and compared it to the DS data. Then, we conducted measurements of the 3D mean velocity and TKE of the CrossJet flow using MRV. Finally, we conducted an analysis involving TKE isosurface and signal attenuation ratio based on MRV measurements. First, I will explain the principle of turbulence intensity measurement using MRV. As you know, the principle of turbulence intensity measurement using PIV relies on calculating the standard deviation of instantaneous velocity fluctuations as a proportion of the mean velocity. However, MRV measurements are based on the phenomenon of signal loss due to intravoxel phase dispersion when velocity fluctuations occur in the magnetic field. So by quantifying the signal loss and using the formula below, we can directly calculate the turbulence intensity. The results are shown in the right figure. The turbulence intensity is usually applied by considering the peak value as important. So as shown in this figure, in the case of Reynolds number of 11,700, there is an approximate relative error of 0.4% when compared the peak value measured by MRV to the DS data. Similarly, for Reynolds number of 37,700, a relative error of 4.6% can be observed. Additionally, KV is flow sensitivity in this formula, calculated as pi divided by bank. Bank is a parameter that we directly set before conducting the MRV experiments. In the case of Reynolds number of 11,700, a lower relative error can be achieved between MRV and DS data at the center region of the circular pipe by setting a higher bank value. From now on, I will explain the experimental setup for the CrossJet flow. As you can see in this figure, we have closed-loop circuit, including pumps, flow meters, flow control, and data acquisition instruments. This experiment used the same geometry as presented in the MRV Challenge 2. Within the geometry, 6 cubical elements are positioned at the wall and channel center. There is a main flow from the left to right and an injection flow from bottom to top. To ensure uniformity of the main flow at the inlet, the flow conditioners and boundary layer strips were installed. Next are the flow conditions and the MRV scan parameters. The working flow used is a 20 mmol copper sulfate aqueous solution. The main flow operates at a Reynolds number of 15,000 with a flow rate of 22.2 rpm. The flow rate of injection flow is 1 rpm. The MRV experiments were conducted using the 3T human MRI at KBSI Wuchang Center. the FOV was 256, 96, 96 mm with a 0.5 mm isotropic spatial resolution. For mean velocity measurement, the bank was set to 110, 110, and 90 respectively. A signal average of 6 was applied with 2 flow-on cases and 1 flow-off case used to calculate the averages. For TK measurement, the bank was set to 30, 30, and 25 respectively. A signal average of 12 was applied with 10 flow-on cases used to calculate the averages. The following is the schematic representation of mean velocity and TK quantification using MRV. As you know, mean velocity measurement by PCMRI is based on the phase difference. However, for TKE measurement, S0 and SKV represent signal magnitude without and with motion sensitivity. Next, using the difference of these two signals, which is the signal loss, turbulence intensity in the x, y, and z directions can be directly calculated through this equation. From now on, I will talk about the results of the flow visualization. First, I will show you the cross-section results of mean velocity and TK data at z-plane. For mean velocity data, the arrow indicates the in-plane velocity, while the contour indicates the out-of-plane velocity. As you can see, a large TKE is generated due to the boundary layer trip and the boundary layer effects near the wall. Then we can observe that due to the influence of injection flow and the presence of cubic elements arranged in the center and on both sides of the channel, a large amount of TKE is generated. Next, I will show you the results at X-plane. Through these results, you can more clearly observe the TKE patterns generated near the wall from the boundary layer trip and the cubic elements. Next, I will show you the results at Y-plane. From this perspective, you can more clearly observe the TK distributions generated when the injection flow merges with the main flow. And next is the TK isosurface result. The left of this slide shows the isosurface results of MRV text section with a value of 20 for TKE. As you can see, a significant amount of TKE is generated in the downstream of the jet flow inlet, cubic elements, and the boundary layer trip. The right side shows the TKE isosurface results for the CrossJet flow region of TKE with a range of values from 10 to 40. We can clearly observe the variation in TKE values from 10 to 40 in the isosurface, with the maximum TK value occurred downstream of the first cubic element after the jet flow inlet. Next is the analysis of signal attenuation ratio in the stream-wide direction. Previous studies have reported that signal attenuation ratio determines the precision and accuracy of the TK estimation. The optimum sensitivity can be obtained by using a bank value that results in SKV divided by S0 of 0.6. So as you can see in this graph, in the region where Z is less than 50 mm, the signal attenuation ratio falls between 0.7 to 0.9, resulting in poor sensitivity for TK estimation. This is because of the low turbulence level in the inlet region, where signal loss has not occurred sufficiently. So in this area, by lowering the bank value, the signal attenuation ratio can be reduced to about 0.6 to achieve good sensitivity in TK estimation. In the region where Z is larger than 50 mm, the signal attenuation ratio is around 0.6, indicating good sensitivity in TK estimation at this region. This demonstrates that the chosen bank value enables accurate TK measurement in the CrossJet flow region. In this study, we successfully visualized the 3D mean velocity and TK of CrossJet flow using MRV, demonstrating the capability of MRV to visualize the flow in such complex and opaque geometries. In the future work, we will attempt the multi-bank measurement method by gathering the best result from each bank measurement to achieve improved TK estimation.